Picking up where we left off on number 14 at the very end of that video, we saw that g of f of x, the f of x we couldn't really evaluate, so we just plugged that formula right in for x squared minus 2 for f of x. You can see that f of x was given to us in the directions. So if we took g of a blank, that would of course be a blank minus 3. I'm getting that from here. Everywhere where we see an x, we just put in open parentheses. So when you plug in x squared minus 2 into these parentheses, you'll see really you just have to combine like terms. Negative 2 minus 3 becomes negative 5. Final answer would be x squared minus 5. Okay, moving on to number 15. Just following these directions, g of x multiplied to f of x, it's the formula negative 2x plus 6. We're going to multiply that to 3x minus 1. The directions tell us to multiply or to FOIL. Negative 2x times 3x is negative 6x squared. Negative 2x times negative 1 is a plus 2x. 6 times 3x is 18x. And 6 times negative 1 is negative 6. So we'll get negative 6x squared. 2x and 18x add up to 20x. And then we have our minus 6. So just follow those directions. There's no way any x value could ever cause an error. You never would divide by 0. You'd never have a negative inside of an even radical. Your domain will be all reals. For 16, g of x would be negative 2x plus 6, but notice the directions tell us to subtract now. We're going to say minus 3x minus 1. We're going to have to distribute that negative. We'll get negative 3x. Negative times negative 1 is a plus 1. Combining like terms, you'll get negative 5x, and 6 plus 1 is 7. So here's negative 5x plus 7. Again, we don't have any way we can divide. We don't have a radical to worry about. Our domain is simply going to be all reals. For number 17, however, this is very different. We're going to say that our top, f of x, is 3x minus 1. The denominator is negative 2x plus 6. So plain and simply, we have 3x minus 1 over negative 2x plus 6. There's really no simplifying that can be done. Can't cross out x's by the order of operations. You just have this for a final answer. But for domain, for the first time we have a fraction. And negative 2x plus 6, we don't want that to equal 0. If what I put a box around, if that became 0, we'd divide by 0, and that would violate a rule of arithmetic. If we type that into the calculator, dividing by 0, the calculator says you can't do that. You get an error message. So solving, I'm saying negative 2x plus 6 can't be 0, minus a 6, divide by negative 2. You'll see that x cannot be 3. If you did plug in a 3, you'd get 0 on the denominator, in that denominator, and that would violate our restriction. We can't have that happen. For number 18, well, f of x is really filling in for y. And the first step in finding an inverse is to switch x and y. Interchange them. Wherever you have an x, write a y. Wherever you have a y, write an x. We're going to solve for our new y. But as we're looking at this denominator of a 4, how about we multiply every part of the problem by 4 to get rid of fractions? It's always a smart thing to do. Makes life so much simpler. 4 times 2, of course, is an 8. You're going to add an 8 to both sides. We'll have 4x plus 8 is equal to y. But an inverse is very special notation. F negative 1 of x. This is indicating that you have actually found the inverse of the original function. For number 19, well, same idea. Replace f of x with y. Now switch your x and your y. And we're going to solve for our y. Well, obviously, I want to get that y alone. I'm going to minus a 1 on both sides. And to get rid of that third power, we're going to take a third root, or a cube root. So we'd say y is equal to the cube root of x minus 1. This would be f inverse is the cube root of x minus 1. Number 20. Thank goodness, a very, very calculator-driven kind of problem. Let's remember how to get the mean and the standard deviation. You have to press the statistics button right next to the down arrow, hit edit. If there is something in there already, let's just say that you saw some numbers, you can go all the way to the top, press clear, hit the down arrow. So I'm just going to type these in now. I'm going to go 72, hit enter, 84, hit enter, 81, 78, and 80, and 86, 70, and 80, and finally an 88. And nicely, we now have all of our data entered. What you can do is, quit, hit stat, go to calculate, hit that right arrow, and then hit enter for one variable statistics. You'll have to hit enter 3 times, and you're going to see your X bar. X bar is going to give you your mean. So it's about 79.9. By the way, we were doing that all the way back in September. But if you look at sigma right here, this is your standard deviation. That's about 5.6. Again, the standard deviation always tells you how much your data is spread out. So, thank goodness the symbol that you see on the calculator is going to be exactly the symbol that they're asking for. Let's go to the back page. You can see very quickly which data is more spread out. All you need to worry about is the sigma. You can see that sigma is larger for set A. So set A is going to have its data more spread out. All right, so very quickly, let's go to our last 2 problems. Again, the calculator is going to come to our aid. We can type in the square root of x plus 3. Make sure you hit the right arrow to move out of the radical, and then you hit plus 1. If you don't move out, obviously that's going to get you the wrong graph, the wrong everything, and that's one of the biggest mistakes. You have to be very, very careful about that. So we're going to go to second table, second graph. And you can up arrow for a little bit. We're looking for friendly points, but I do want to point out that you do get quite a bit of errors. You get errors until you get to -3 for your x. So for -3 for your x value, okay, so again, looking at the calculator, you're going to be able to notice that you're getting some friendly points like -3, -1. You can see it looks like we were at -2. You can see that's going to be at, or actually -3 comma +1, but -2 comma 2. You can continue to scroll down a little bit here. You can see you're going to be at 1 comma 3. And it looks like we're also, if you want to go a little bit further, you could be at 6 comma 4. And the wonderful thing is, not only do you know that these points are in fact on your curve, if you press graph or press zoom 6 to make sure you're on a standard window, you're going to be able to see the general shape of that curve. So we can say 3 to the left, up 1. 2 to the left, up 2. Here we go 1 to the right and up 3. You can go 6 to the right, 1, 2, 3, 4, 5, 6, and then we go up 4. And real nicely you get this kind of a general shape. But the domain and range, just want to point out again, all the errors that you saw. The first time you don't get an error is when x equals -3 and when y equals 1. You're going to be able to say that x is bigger than or equal to -3 and y is bigger than or equal to a 1. As you slide this over, you can see that our x values get larger than -3. They don't get smaller. Same thing with our y values. We can get larger than a 1. We don't get smaller. As we take a look at our last problem for number 3, the wonderful thing is, for cube roots, we can immediately say that our domain and our range are all reals. You can always say that for a cube root. But let's get some help knowing what this thing looks like. Hit clear, we'll hit math, bring down that third root, we'll type in x minus 2, slide that over, hit -1, and if we went back to the table, just hit second table, again, what you notice is you don't get the error messages that we see with square roots. You'll find friendly points. It looks like we'll have something at -6, -3. As I scroll down a little bit, looks like we'll be at 1, -2. Looks like we'll be at 2, -1. And if we kept going, we'll be at 3, 0. And then 10, 1. So I can go 6 steps to the left, 1, 2, 3, 4, 5, 6, go down 3. 1 to the right, go down 2. 2 to the right, go down 1. Go 3 to the right, don't go up or down any. Here's 4, 5, 6, 7, 8, 9, 10. Just go up 1. And of course, you could hit graph, and you get that kind of an S kind of a shape, and very nicely you're going to be done. So this is what our test is going to be looking like. Domain and range are always going to be all reals for cube roots.